Welcome, and thank you for joining the fifth session of this series titled NVA High Availability Options in Azure, the Art of the Possible. My name is David O'Keefe, and I will be your host for today. The session is being recorded. If you don't wish to be recorded, please drop now, and you can watch the recordings later at aka.ms/AZ networking sessions. During this session, we will share a link to collect your feedback. The feedback is only 4 questions and it will take you less than 60 seconds to complete. We do use this feedback to make adjustments to these sessions, so please continue to let us know what works well and where we can improve. Agendas, FAQs, and feedback forms for the sessions, as well as the recordings and additional materials, can be located at aka.ms/AZ networking sessions. Here is the agenda for today. We'll immediately jump in with Nehali to discuss NVA high availability options in Azure, and we'll finish up with a deep dive session on advanced scenarios with Azure Route Server and vHub with Jose Morano. As a reminder, here is the core team developing this content, organizing, and producing these sessions. We'd like to say a huge thank you to our moderators supporting us today. Remember to leverage the Q&A panel throughout the session to ask your questions. Here are your presenters for today's sessions, Nehali Blog and Jose Morano from Microsoft. Without further ado, I'll pass it over to Nehali to kick us off. Nehali, take it away.
Thank you, David. Let me share my screen. Hi, everyone, and welcome back. Thank you again to our moderators for supporting the live event for the 5th week in a row. And I'm super thrilled to have another one of my esteemed colleagues, Jose Morano, to co-present with me today. So thank you, Jose. So what you are seeing on my screen is just a little backstory on the inspiration behind this networking series and the layering methodology. This is a real NVA high availability design that I did back in 2020 to mimic a customer scenario. And as you can see, it got very complex very quickly. So this is the first design that I did in Draw.io, and let's untangle it with layers. So I will say that this session is one of the more complex and advanced of the sessions that we've done so far. It would start mostly at level 300, 400, goes into 500, all 500 with Jose. So it's not a substitute for Azure Docs or how-tos or hands-on labs, but these sessions are designed to go over the options, the use cases, and discussing the pros and cons. So let's start with the concepts to level set the discussion, as I will be using these terms quite a bit. Again, it's a layer, so if you're familiar with these concepts, and you can always hide the layer. So real quick, in this diagram, you see that I have 2 firewalls, and I'll go through this 9 elements, the 9 concepts, and they're all numbered. So we'll start with number 1. Which is the 2 firewalls that inspects the traffic to and from. So you want to look at the untrust side and then the trust side, right? The public and the private side. Then we talk about inbound and outbound. When you're thinking inbound and outbound, think perspective. So from the perspective of this server, which is in the data center, this orange flow is inbound. And from the perspective of this home user, the green flow is outbound. All right. And then SNAT, or the source net, when this user in a home environment goes out, it gets seen with the public IP of the external interface. That's the source netting. And same way, if it's the server behind a firewall, in this scenario, the SNAT is the trust interface of the a firewall. So the IP of the trust interface of the firewall. All right. And for number 6, to understand the stateful firewall, it's important to understand the TCP connection and the handshake. That's what this output is showing. And all of the bold items in this packet captures are part of the same TCP connection, which uniquely identifies that connection. So that's called the 5-tuple, and our load balancers use the 5-tuple hash algorithm. And lastly, last concept number 9 is actually I missed one, which is the DNET, the destination netting. Number 4, destination netting is used if you have a server, let's say with a private IP, it does not have a public IP. You would want to net the public IP on the firewall to the private IP on the server. That's destination netting. And then the last concept here is the one where imagine that this was your data center and you were used to having high availability for your physical firewalls. Some of those traditional methodologies don't work in Azure. I've put a link to the FAQ to explain why, so be sure to check that out. With that, let's turn off the concepts and let's go into our first base design. Like we've done in previously, we'll start with the basic out-of-the-box default design, and then with layers, we'll go into more complex and understand the why behind using different options. Right. So this is a review of what we have already done so far. So let's say that this was your classic hub spoke design. The green flow is referred to as the east-west flow, and it works by the virtue of having the use remote gateway and allow gateway transit on this peering. And then the orange flow is the north-south flow going out onto the internet. So let's introduce the firewall. Now, from a placement perspective, the NVA and the Azure firewall, so if I light up the NVA, NVA and Azure firewall sit in the same place on the network, right? So it's important that we peel off the NVA layer just real quick to understand how it works without the NVA, and then we will introduce the NVA. So as you saw, when I introduced the firewall, the goal is to steer this orange and the green flow through the firewall. So let's see how we can do it. To do that and to preserve the flow symmetry, we have to create a subnet, a route table on all of the spoke subnets over here. And then for the return traffic, we also have to create a UDR or a route table in Azure so that the return traffic also goes through the firewall, right? So when we introduce the firewall, flow symmetry becomes very, very important. So then how does Azure Firewall do this? So we'll understand this concept first with Firewall and then with NVA. So you can see that this is not south incoming, right? So incoming to Azure. So this user initiates the traffic. So this animated flow is showing that this user initiated the traffic. It hits the Azure firewall, and notice that it does an SNAT and a DNAT to the load balancer IP, right? And this SNAT ensures that the return traffic, the dashed line, goes back to the firewall. So that's the north-south incoming. Let's look at north-south outgoing. So again, outgoing from the perspective of this VM, it follows this UDR, the quad 0 route to the firewall. And then from there, notice how it gets SNATed to the public IP of the firewall, and that ensures that the return traffic comes back to the firewall. So that's the north-south outgoing. Now let's look at east-west. Again, the terminology east-west is over here between on-prem to Azure or Azure to on-prem. So in this case, we're showing that this VM is initiating the traffic going to the Azure side. And if you follow this flow, it goes over the express route, and when it hits the gateway subnet, this UDR steers it to the firewall, right? And then it reaches, of course, the load balancer and the VM, and the return traffic again uses the UDR. So UDR, again, very important for flow symmetry. And then we see the same flow in the reverse direction. Um, when um, when you use east-west with the Azure firewall, there is no SNATing, and it is an important point, and it is a best practice to not SNAT the private traffic for various scenarios that involve domain controllers and Kerberos authentication and other mechanism that don't support SNATing. So important to know that Azure Firewall does give you that capability. Now, let's introduce, now that we know all of these flows, let's introduce the NVA. NVA would sit in the exact same place where the firewall does, and all of this traffic will be processed by the NVA instead of the firewall, right? So imagine that this NVA fails. So all of our traffic will break, right? So there is no SLA for single VM in Azure. Of course, you could do a premium disk and high availability zone, but it's nowhere near enterprise grade reliability, right? So the fact that this NVA is so central to all of the traffic kind of sets the stage for why a high availability, right? So let's go into our next option. Let me light up option number 2. I will say that before we go into the rather complex NVA high availability and the LB sandwich design, often referred to as the sandwich design, let's explore all of the options, right? So we talked about this in our expert session with Jose and Heather in one of our first session, right? Simple sometimes is good if it solves our use case, right? So let's see what other options do we have. So we'll start with an active NVA, and we introduced a standby NVA, right? So only one is active at any given time. Second one is waiting, ready to go. So still there is a failover orchestration that needs to happen, and the UDR rewrite needs to happen. So when this NVA fails, you still have to rewrite the UDR to point to the standby NVA, right? This orchestration is done using Azure Managed API calls, and it takes greater than 15 seconds. It's too long for production workloads. So this is no longer a recommended method. The reason I bring this up is some vendors may still have this on their website, but be sure to check out other options, because this is no longer a recommended approach for active standby failover because of how long it takes. So then there is another intermediate option where we could have two NVAs with an internal load balancer in front of them. And notice the internal load balancer has HA ports enabled. So what happens is the UDR always points to the IP of the internal load balancer. So in the event of the failover, so if this firewall fails and it goes to this one, you don't have to do the UDR rewrites, right? So in that sense, it saves you the time, and this is still used in production in some cases. Of course, you can egress using this NVA using a public IP on the NVA. You can drop a instance level public IP, or you could use the NAT gateway for egress. All right, so that's active standby design with internal load balancer. And let's look at some of the PaaS options, right? So we looked at the Azure firewall already. We looked at how it was central to all of the flows. The other options are if you have web workloads, you can use a web application firewall that comes with application gateway. And for smaller scenarios, you can also use network security groups, right? So for small customers, you could probably just use network security groups. So this is showing you all of the PaaS options that are available to you before you consider an NVA high availability design. And I took this screen capture right out of one of our blogs, a tech community blogs. It does a comparison of Azure Firewall to NVAs. And one of the biggest thing that I want to call out is Azure Firewall has a built-in high availability and of course the cloud scalability. And with NVAs, you have to implement VM scale set. So, vendors bring in their own templates and orchestration for NVAs. And there's also a cost comparison in that same article. And we continue to invest in the features in our Azure firewall. All of the next gen features that are available in NVAs also are available with Azure Firewall. So be sure to check out the latest features for that. So now that we know all of our other options and what they bring, let's look at the NVA high availability, the sandwich design. Now let's understand the why behind or the use case for this design, right? So we saw the PaaS option, we saw the IaaS versus PaaS comparison. So when would you use this, right? So the use case is, let's say your security team has made investments with a security vendor, or if there are certain features that you need that are not available in Azure, or if it's a skill set that you already have. So those are the classic cases where you would want to use high availability, this design that we're going to talk about. And remember that I have chosen to demonstrate the NVAs, which are firewalls, the stateful firewalls, but you could use the same design for other SD-WAN or layer 7 load balancer or IPsec termination devices, different type of NVAs that are available. The most complex ones are the stateful firewalls, so we will be looking at that. So what happens in this design is that you have two active firewall, two or more, right? And it gives you that enterprise grade failover and of course the scalability that you need. So let's look at all of the components in this design. This is often referred to as the load balancer sandwich designs because you have the two load balancers and the NVAs are in the middle. So let's look at all of the components. So the blue lines that you see are the load balancer probes. Notice that the internal load balancer has HA ports turned on, meaning that you can load balance all of the ports. The top external load balancer can be done with or without floating IP. I did a lot of coverage on floating IP in my load balancing session. And then we have this quad 0 UDR that is pointing to the internal IP of the internal load balancer. And then we have gateway subnet UDRs that are also pointing to the internal IP of the load balancer. Of course, be sure to leverage your vendor templates when you deploy this. I was working with Checkpoint last month, and they have a template that does the whole deployment, including the two load balancer and the NVAs that scale automatically. So it is important to depending on which vendor you are using, that you leverage that vendor's template for best practices. Okay, and in this design, the flow symmetry is preserved using the 5-tuple hash that we looked at in the concepts, right? So these are the various different components of our design. Let's look at all of the flows, and we'll look at each one of them separately. So first, we look at east-west flow, which is from on-prem to Azure. So initiated by the VM on-prem, reaching something in Azure. So let's take a look at that flow end-to-end. So this VM initiates the traffic. It goes over express route or any private connectivity. It hits the gateway subnet. Gateway subnet as a UDR pointing to the internal IP of the internal load balancer, and that 5-tuple hash algorithm kicks in. It picks this NVA, and notice that this NVA is not doing any SNATing, and it reaches this VM. The return traffic will follow this UDR and will hit the this load balancer. Now, it is still going to have that same 5-tuple, so it would pick the exact same NVA. And that principally is very important to know, that how that flow symmetry is preserved, and then the rest of the flow back to the VM. Okay, so that's east-west from on-prem to Azure. Now we look at east-west from Azure to on-prem. So again, that's the initiating VM is this red VM in Azure, and it follows this UDR, hits the load balancer, and then that traffic gets routed over the express route. Again, no SNAT in this design, and that is the desired behavior best practice design, to not use SNAT for east to west. So let's now look at the north-south inbound. Now, north-south inbound is the traffic that is initiated by the user out on the internet coming in to our VM. This is one of the more complex flows, so let's take a closer look at each element of this flow. So this user first hits the public IP on the load balancer, and the load balancer, let's say, happens to pick this NVA. Notice that when it leaves the NVA, it has to do both the SNAT and the DNAT. All right, so this flow from the NVA to the load balancer is SNATed to the private IP of the NVA. And then let's say it picked this VM, the return traffic now bypasses the load balancer because of the SNAT. Now let's say that you forgot or you missed configuring the SNAT. What will happen if you missed configuring the SNAT, and this is a critical concept, is that this return flow, this green flow, instead of bypassing the load balancer, it would follow the UDR. And when it follows the UDR, this load balancer had no idea about the 5-tuple hash, so it would just happen to pick this NVA, right? Because the first flow landed on this load balancer, and the second flow is landing on the different internal load balancer. So when that happens, this NVA does not know about the first packet, the SYN packet. So you will see on your firewall, and I took this capture from one of the checkpoint firewall, but this second firewall will reject the traffic saying, I'm seeing the SYNAC packet, but I didn't have the SYN. So it will drop the packet and the flow will break. All right, so this is a very common mistake that I've seen in the field. So wanted to call that out. And so be sure to kind of make sure that the flow is symmetric end to end. And then the last part, the last flow is the one that is outbound, so initiated by a VM in Azure going outbound. That will follow this UDR to the ILB, and then from the ILB to it picks the NVA. And notice that there is SNAT in two places. The NVA does the SNAT and also the load balancer. So the return traffic kind of follows that path. So SNAT makes the return traffic to be symmetric. All right, and there are a few. Oh, and the last part of the flow, I'm sorry. So the return traffic will come back to these NVAs, and then the last part of the flow will bypass the LB because it has routing to the subnet where the VMs reside, right? So that's how the flow works. And then there is a slight variation to the outbound, and I'll show you different vendors do this differently. But you can also put an instance level public IP on your NVA to egress out of Azure. Or you could put a NAT gateway here um, that you can attach it to the firewall untrust subnet, and you can egress using the NAT gateway as well. All right, and so a couple of things over here. I did do in the load balancing section. I did show you, a variation or a different way of doing this load balancer sandwich design using the Azure Gateway Load Balancer. Again, that Gateway Load Balancer is only going to help us with the north-south flows, right? So not the east-west flows. The east-west flows, these two flows, still would require this design. So I'm going to spend just a couple minutes on the gateway load balancer, just for the completeness of this demo. So let's, if you want to do a deeper dive, it was in my load balancing session that we did a deeper dive of gateway load balancer. So here, there is a lot to see here, but this screen may look familiar to you. So imagine that this is the workload that you want to protect, and you would do that using your NVAs that are highly available NVAs, but you would put those NVAs in front of the gateway load balancer, right? And remember that most vendors give you a template that would deploy this whole pink box with one ARM template. So be sure to leverage that. And the way the flow would work is the gateway load balancer uses the concept of what we call the service insertion or bump in the wire technology, right? So I'll show you quickly the inbound and the outbound flows. So the flow that's initiated by this user will first go to this external load balancer. And again, this is the protected side. So that this is the protected side of the network that you want to insert the firewall in. And then we will chain this load balancer to this gateway load balancer. All right, and that's how it is working. And similarly, outbound flow will go through this instance, NVA instance. It would get cleansed and go back to the internet, right? So both the inbound and outbound flows, if you want to see it together, they are getting intercepted, so to speak, by the security appliance, and they're applying the policies. And if you want to see how that works behind the scene, again, this is a total deep dive over here. Behind the scenes, we spin up two VXLAN tunnels. As you can see over here, we spin up these two VXLAN tunnels that connect the load balancer to the NVAs. And the way it is it works is in the portal, we give you the option to specify the internal and the external port, and that's what builds these VXLAN tunnels. And the identifier that you punch in the portal is the VNI, the VXLAN network identifier. Again, I've done a very simple yet conceptually explaining VXLAN blog. There is a link to it if you're interested. Do check out the FAQ document. So with that, it completes my part of the presentation, and I'm going to turn it over to Jose.
All right. Thank you, Nehali. Right, let me start sharing my screen. Here we go. Share. All right. Okay, there we go. Fantastic. Is there any question in the chat that we want to answer before moving into the live demo?
No, I think we're good, Jose. You can continue.
All right, excellent. Okay, so yeah, we prepared a bunch of demos for you for today. It's going to be tough to get through all of them, but we will do our best. So essentially, we have two main environments. We have a hub and spoke environment and a virtual one where we have a couple of different topologies with NVAs. Let's see what we can go through. As you can tell by the amount of concepts that Nehali told, there's a lot of ground to cover, so let's start with that. First of all, the first scenario that we would like to show you is the NVAs with so-called floating IP. So essentially, where we have sorry, and this is the main lab topology that I will be using for the hub and spoke scenarios, where I have a couple of spokes, one hub, and simulating on premises via a VPN tunnel. So in this case, if we have two NVAs, one common way of grouping them is by having IP addresses that can move or float across each other. For example, you see that here the .61 IP address is currently in NVA1. And NVA1 is the only one with a public IP, which is what would attract internet traffic. If NVA were to fail over, then the IP would move, the private IP would move, and the public IP would move as well. So the way that routing looks like is typically, if you look to the right side of the screen here, I have the effective route table here for one of my spokes, and this is pointing to the .61. So essentially to this one, to the private IP address that can move back and forth. This is a user-defined route, and essentially this is what you would have as well in the gateway subnet, right? So that the traffic is symmetric. Normally we don't recommend this setup because it takes a bit to update this. So let me show you. If I'm, for example, now let's double check where my IPs are currently configured. So I have them in NVA1. As you can see, NVA1 has this one plus the floating one and the IP. So what I'm going to do is I'm going to initiate a ping from spoke 1 to spoke 2. Let's check. I'm in spoke 1. That's the 17 exactly. So let's ping. I think I have it here exactly. If I ping this one, then I will start moving the floating IP to the number 2 appliance. So essentially, these NICs that are associated to the VMs, they have so-called IP configurations. The way to associate a secondary IP is to have a second IP configuration. The public IP is as well configured in that configuration. So what I'm doing in this function is 2 steps. First, you need to remove the IP configuration from the failed appliance, assuming that it has failed, and then you put it in the secondary. This code typically runs inside of an agent in those NVAs. As you can see, there was a bit of a hiccup there. It was a couple of seconds. This is not too realistic because essentially moving the IP between two healthy appliances. Normally what would happen is this one would, the primary would fail, and then the agent running in the secondary would recognize that and would initiate these calls. These calls are calling the ARM API, the Azure API. And you can see here that the whole process of removing the IP configuration from the failed NVA and putting it into the active one is around 1 minute. Let me stop this and see how many we. So essentially, we transmitted 89, we lost 61, so we lost around 30 seconds of traffic, give or take. So as you can see, it's a very simple scenario, a very simple topology where the complexity is absorbed by this agent, and the main by this agent running inside of the NVAs, and the main downside is the convergence time. What we can do now is, instead of doing this, is we could just move on to the load balancer sandwich that Nehali talked us about, right? And here the routing would look like, let me scroll a bit here to there so that we can see everything. So we would have that public load balancer, that internal load balancer, and then routing in the gateway subnet, and the spokes would be pointing to that IP address, and the load balancer and the load balancer would provide traffic symmetry. Frequently asked questions is whether you configure the public load balancer with floating IP or direct server return or not. It typically doesn't matter too much for the NVA itself, but there's an important distinction, which is if you don't do direct server return or floating IP here, it means that the NVA will not see to which IP address the call came. So if there are multiple IPs there, you do need direct server return or floating IP. So it tends to be a best practice by most NVA vendors I know. Convergence time here would be quite faster because the probes in the load balancer would be typically, and I can show this maybe in the portal. Where do I have this? If we go to the load balancers, do I have one here? Yeah. So when you configure the gateway, when you configure the probes, you can define the timers, right? And for example, here I'm using 15 seconds, but you can get down to 5. So if you do 5 seconds per probe, 3 probes need to be lost, then it's between 10 or 15 seconds convergence, which is much better than the around 1 minute that we saw here. And take into consideration this is only the failover time. You need as well to recognize that the other appliance is dead. So the load balancer would give a much better convergence time normally. I'm not going to spend much more time here because we would like to cover as well the scenarios with the route server. What I'm going to do now is I'm going to go back to the portal. I'm going to go back to that route table I have assigned to the spokes. This is my spoke VM route table. As you can see here, I have a default route pointing to that floating IP from the previous scenario. I'm going to delete that. And I'm going as well to make sure that I'm propagating gateway routes here. Why I'm doing this? Because in this case, I don't have any more this scenario with the load balancer. What I have is, let me remove this routing here, is I have 2 NVAs in the hub, and they are speaking over BGP with a route server, and this route server is injecting routes into the spokes. So that's why I removed here the gateway propagation, so that this route server can inject the routes. Let's see what this looks like. So if I go again and have a look at the effective routes of the spoke. Now let's hope the demo gods are still with me. It always takes a couple of seconds because the command actually goes to the NIC and retrieves the program routes. So we are seeing here that there are two routes configured, and the default gateway are the .36 and .37, the IP addresses of the NVAs. We see that the routes have a type or a source of virtual network gateway. This means that they have been injected by either a VPN gateway or an express route gateway, or as in the case here, Azure Route Server. This is a very effective scenario if we have we can simulate here a failure of one NVA. For example, if I go to let's go to one of the NVAs. In this case, I will go to NVA 1, and I will kill BGP. System CTL stop. I'm using BERT as a BGP. I'm going to go back and recall the effective routes of the VM and see what happens. The one for 36 should go away, and as you can see, the system was even quicker than me trying to retrieve the routes, right? So the convergence time with BGP is really quick. If I start it again, then when we go back here and redo the command, then we should see that second route popping up. The coming back takes a bit longer, so it might be that I have to do this a couple of times until we see the route there. But it's the other direction that is more important, right? That when an NVA fails, the route is taken away. This scenario is very good for stateless NVAs, normally SD-WAN appliances. Why? Because this can potentially originate asymmetric traffic. In order to achieve an active-passive scenario with BGP, you can do that as well. You can, if I go, for example, to the NVAs and I modify, I'm going to modify the secondary one to send less preferable routes. So I'm going to edit my BGP configuration. This might look like very complex, but it's actually not too much. Essentially, the only thing it's doing is prepending some autonomous system number to the BGP advertisements, so that here I need to restart BERT. So that its route it's less preferable. So if I didn't do anything wrong, then now the route coming from 36 is better than the one coming from 37, or the one from NVA 1 is better than from NVA 2. So now if we do again the effective route table, see. Then the 37 one should be gone. Exactly, there we go. And now we can do exactly the same as before. I can kill here BGP and see what happens. Now this route will disappear, but don't forget that we still have the other one from NVA2. However, it's not preferred. So what should happen is that the .36 route should go away, and then the .37 should kick in. So let's see again how quick Azure is to put this. Again, this could be a little slower than the previous test because now it's two operations. It's removing one route and inserting another one. Drum roll, but it was really quick. You see here that it was much less than 15 seconds, right? It was around 5 seconds. So this is one of the advantages of route convergence with BGP. It's the fastest convergence mechanism that we have. It's more complex, definitely, than the load balancer sandwich, but it's quite faster. Now, I mentioned earlier that this is good for SD-WAN appliances or stateless appliances. What happens with stateful appliances such as firewalls? Well, What you can do is combine the load balancer good things, the load balancer attributes with this one, where you can set a load balancer in front of these appliances. And instead of advertising as next hop the actual IP address of the machine, we can advertise the IP address of the load balancer. So again, quite an easy configuration to do in BGP, depending on the system that you have. I'm going just to do it here quickly. What I'm doing here is I will uncomment this line that will set the next hop as the .62 IP address, which is the one from the load balancer. Save this. Let's restart paired. I'm going to leave the other one without modification, so we should still see the one coming from NVA2. Another drum roll. So essentially then both NVAs would be advertising the route to the load balancer. And then, okay, now the route disappeared for some reason. And maybe I did something wrong. So that's where the demo codes have abandoned me. So let me do the other one as well. Azure log, conf, here. Azure system starts, right. Okay. So not sure what's going on, but yeah, they probably did something wrong in my BGP configuration. Those routes should come back again with the .62 as next hop. Let's see. Let's give it one more chance, and if it doesn't work, I will move on to the next topology. There we go. So now, even if we are advertising two routes, and even if the two routes would be equal, we would only see one of them here because both are identical with the load balancer as next hop. The nice thing about this one is if one appliance dies, the topology doesn't change. The routing topology doesn't change. I mean, it's only the load balancer that decides to forward traffic to the other one. Of course, in this case, the convergence times is the load balancer convergence time, since the routing topology stays constant. Okay, we have a small issue here, and you, if you've been putting attention, you might have figured out. So here in the active routes, we are seeing, sorry, in the effective routes, we're seeing only this default route. Because I enabled gateway propagation in the gateway, in the route table. However, we are not seeing the VPN gateway route. Why is this? Well, it's because, as I was mentioning earlier, there are different patterns depending if your NVA is an SD-WAN appliance or a firewall appliance. For example, the NVA appliance often needs to advertise prefixes to ExpressRoute or VPN. And the firewall appliance often needs to advertise prefixes to the spokes, like in this case. What if you need to do both, right, but not at the same time? So this is where there's a particular pattern here where you can have a second, let me remove these layers and go here, a second route server, and this is actually my topology. I was messing around with you a bit because I didn't show you this one. In this case, when my NVAs behave as a firewall, they advertise the 000, the default route, to this route server, and this route server then pushes that one to the spokes. However, when my NVAs are behaving as SD-WAN, and they want to advertise something to ExpressRoute or to VPN, they advertise it to this other route server, and this route server propagates it upwards, so that the two routing planes to the spokes and to ExpressRoute and on premises in general are cleanly separated. If you don't need this, you can replace this with UDRs. That's perfectly fine. Because as we said, the Azure firewall typically, or any firewall typically is stateful and needs to have a symmetry provided by the load balancer. So in this case, BGP is not providing better convergence time, but potentially better ease of use, since you don't have to configure those UDRs. But this one to advertise prefixes from SD-WAN to on-prem is often non-negotiable. unless, of course, we move on to virtual one, which would be the next topology that I would show. Exactly. I think we are done with this. Before doing that, I would like to check with our great Q&A managers whether there's any question in the chat that I should answer before moving away from the hub and spoke scenario into virtual one.
Jose, one question for you. Why does the UDR for the spokes not contain routes for the peered VNets? With only a quad 0 route pointing to the NVA, the traffic destined to the spokes will bypass the firewall.
So let me try to answer that. So if, say, let's say the test I was doing earlier, where I was going from spoke 1 to spoke 2, I'm going from 172.17 to 172.18. As you can see in the effective routes of the spoke, this spoke 1, it doesn't know 172.18. So when I have this route here, it covers as well for 172.18, meaning that the only way that spoke 1 has to reach spoke 2 is to go over the NVA here. There's no way that spoke 1 can bypass the firewall there. If we check the routes for spoke 2, we will see something very similar, where instead of 172.17 for the local VNet, you will see the 18. But similarly, spoke number 2, there we go. Spoke number 2, there's no way it can reach spoke 1 if it's not over this route. So there's absolutely no need of specifying here the spoke, the other spoke VNets. The one place where you do have to do that is in the gateway subnet. Right, in the gateway subnet, you do need to override each spoke VNet because the gateway subnet does know about both spokes since they are directly connected to the hub. In let's say in a normal topology, not in this weird thing that they have with the two route servers. In this more normal topology, when these peerings are configured with use remote gateway, then the gateway needs to override those. Yeah, exactly. Hope that answers the question.
Yeah, thanks, Jose. Go ahead and proceed.
Perfect, thank you. Okay, so in virtual one, we have a couple of possible topologies that we would like to show. In this case, it's not going to. We are not going to use the CLI, so I'm going to give you some rest there. Thanks for bearing with me with these cryptic commands. What I have here is, where is my virtual one? There you go. It's a virtual one with two hubs, and I'm going to explain what we have here. So let's do this a bit larger. Okay, so we have two hubs, and we have 3 sets of NVAs. We have on hub 1, we have an NVA here on a spoke. And this NVA is propagating 2 additional segments, is 10.131, 10.132. What this NVA is using to propagate this is eBGP peering directly to the virtual one hub. Why is this important? Because similarly to what we discussed earlier, when you are propagating routes with BGP, there is no guarantee of traffic symmetry. And the trick we were using earlier in hub and spoke to set the next hop of our eBGP routes pointing to a load balancer cannot be used yet in virtual one. We are working on bringing this in the future, which means that you can potentially have asymmetric traffic here, which essentially makes this pattern not so useful for firewalls. On the other side of the diagram, we do have a firewall here, and we have one second, a load balancer in front, and since we want to send traffic to that load balancer, we are using static routing here. So in other words, you can define static routes for these 2 segments here, and these 2 indirect spokes, so to say. so that because the virtual one hub will not know about them since they are not directly peer to the hub. So the virtual one hub needs to know where to send traffic to those, and it will send it to the load balancer. Here, these spokes will have again UDRs pointing to the load balancer as well, and there we will have the symmetry that Nehali was talking about in the first part of the session. Secondly, we have a set of NVAs integrated inside of the virtual one hub. So not as the other two ones that we saw already. We have two NVAs integrated inside of the virtual one hub, and in this case, they are simulating an SD-WAN appliance that is supported in Azure, such as Cisco, Viptela, such as Versa, such as Fortinet, VeloCloud, and I'm probably forgetting someone. Please forgive me if I do. The list is, of course, fully documented in our docs. So what these two NVAs do when they are deployed over the portal is speaking BGP to this internal router inside of the virtual one hub and propagating the routes there. So let me show you all this. We have 4 minutes, so it's going to be fun how we describe all this. If we first go to Hub 1, in Hub 1, what we have is this SD-WAN appliances peering over BGP. You do that in the virtual one hub. In this case, I have 2 of them, so I have 2 peerings, one to each. So I'm going to get the 2 routes pointing to each appliance. So we will have a very similar scenario as we had earlier with hub and spoke, very quick convergence time. But the risk of asymmetric traffic. By the way, I didn't mention this, but the way of achieving quick convergence is by decreasing the keep alive and the hold timers in your BGP adjacency. We have here we default to 60 and 180 seconds for the negotiation, but if the NVA proposes lower timers, like for example 5 and 15 is what I normally recommend, seconds, then the BGP session will go to that. I think we have no minimum, so you could even go down all the way to 1 second of keep alive and 3 of hold timers. But of course, as always, with lower BGP timers come a higher risk of network instability. So be careful with those. Let's go to Hub 2 here. In Hub 2, what we have is those, let's scroll here, those static routes to the firewall there. So those would be configured in the route table. If the portal is merciful with me, we will get the chance of doing that. So if we go to the route table, we see here that we have these 2 spokes there specified. You can use as well a summary there. There's nothing preventing you from doing that because, again, Virtual One doesn't know the exact networks of this one. But in this case, I just put the 2 spokes. And for the other one, if we go to the network virtual appliance section, this could be again a Cisco Viptela, VeloCloud, anything which is supported. I'm using a test NVA, which is nothing else than an Ubuntu machine, but for our purposes, it will be enough. Right. So the last thing to show before we are at time is what the effective route table looks like, which is going to be a fun exercise in 2 minutes. So let's take the default route table, and I'm going just to highlight a couple of things here when the routes come up. But definitely this is your, the effective route tables in Azure are your best way of troubleshooting, especially if you haven't configured a secure hub. So if we go to the first appliance here, the 10.131, 10.132, you see that we are seeing these routes. Remember, these were in Hub 1, we are looking at Hub 2. So we are seeing these routes prefixed by 65520. Sorry, here 65520 because they are coming from a different hub and they are originated in the 65013, which is our NVA. So Hub 2 would have connectivity here, no problem. If we go back to these ones, we see the 10 to where are they? 10 to 31, 32. They are static routes. You don't see any AS path because they are static. So this is boring. And we see the 1053, which is the branch coming over SD1 somewhere here. There you go. Coming from this, I forgot to put the highest number from the NVAs, but it's 65. 102 is this one, and 504 will be that one. What is interesting is that the routes appear to come from the site-to-site gateway. This is a cosmetic bug we are planning on fixing, but they are actually coming from the NVAs, right? And you can tell that from the outermost system number. And with that, I'm saying we are at time. So David, if you want to close the session, that would be great.
Great. Thanks, Jose. Thank you all for joining us today. Please take a moment to fill out the feedback form posted in our Q&A. And as always, please remember to visit aka.ms/AZ networking sessions for the content covered today. Thank you all.